In this, I'm going to show you how I would attempt this question here from NCEA in 2012, Level 2, Structure and Bonding. First thing I have to do in this table is to identify the types of substance that these actually are, before I can even work out what types of particles or attractive forces are. So my types are, I've got metallic, I've got ionic, I've got molecular, and I've got covalent networks. So if I have a look at it, anything that's made up of two nonmetals like NH3 and like SiO2 has to have covalent bonding somewhere in there between the nonmetals. So that means they can only be molecular or covalent networks. So how do I tell them apart? Well, I am actually expected to know that something like ammonia, like water, like ethanol, that sort of thing, are molecules. So I should be able to write in my type of particle here for ammonia is molecular. Now if you look at SiO2, it's pretty similar to CO2, so you'd be tempted to put the same thing, molecular. But if I look down a bit further, I can see that it says silicon dioxide has a melting point of 1770 degrees Celsius. It then says that this is a high melting point. Well, molecules don't have very high melting points. So it can't be molecular, so therefore it must be a covalent network. Sorry, I wasn't meant to write that in there. So I now know that this is molecular, this is covalent network, and then zinc, I would really hope that we could see pretty quickly that from the options there, metallic, ionic, molecular, covalent network, we should know that zincs are an example of a metal. So now I can start answering my question. Molecular substances are made up of molecules. Molecules are held together by intermolecular forces. Zinc is a metal. Now the particles here you could say are atoms, and that makes explaining their inability to be dissolved quite easy. Or you could call them cations and valence electrons, or a sea of valence electrons, which helps explain their electrical conductivity better. In a table like this, either are going to be accepted. Because of the habit I've got into, I'm going to call them cations and valence electrons. Actually, I might say sea of valence electrons. The attractive forces there, it's a metal, so they are metallic bonds. Silicon dioxide, now this one's a bit tricky. Whenever you've got a covalent network, just get into the habit, this means that they are atoms. They are atoms held by multiple covalent bonds. And that multiple covalent bonds thing is going to become very important in the next question. Okay, so the first step there was working out what type of substance they are and then filling in the table. Moving on to B. Silicon dioxide has a very high melting point. So high melting point means that there must be strong forces in between the particles. And so that's the key thing we're after there. It must require a lot of energy to break these bonds. So a high melting point means a lot of energy is required to break the forces or the bonds between the particles. And that's linking to our question because the question says quite clearly, whoops, sorry, it's meant to be on highlight, not on pen, particles and forces. Okay, so I have to link to those. Okay, so the silicon and oxygen atoms are held together by multiple covalent bonds. In a 3D network. And I'm also going to explicitly say covalent bonds are strong. Okay, so now I've got my answer. I've said what it means, the importance of it, a lot of energy required to break the bonds or forces. I've also said what those particles are, silicon and oxygen atoms. I've also said that it's covalent bonds and that there are many of them. Okay, now move on to C. So hopefully we've tried to race through that one in the first 5 minutes. We want to spend a bit of time on C. And you'll see here we're contrasting. Just set that up again. There we go. So doing a contrast. What that means is we're looking for excellence here. And we're looking at the properties of electrical conductivity, and we're looking at solubility in water. Now, the way I like to answer a question like this is I start by, I have a zinc column and I have a zinc chloride column. Because what I find then is it's very easy to keep my thinking organised. So zinc. Zinc is a metal. Zinc chloride is ionic. Okay, what does that mean? That means zinc cations in a sea of valence electrons. It means metallic bonds holding zinc particles in place. Ionic, what does that mean? It means, it means Zn2 plus and Cl minus ions held in place by strong ionic bonds. Okay, there's something they don't both have in common here. This is a 3D lattice, and actually so is a metal. That's actually a 3D lattice as well, or metallic lattice. And I'm just going to put lattice in brackets here because I'm looking at the space I've got left and I'm running low on it. Okay, so now I'm going to talk about the two properties and link those to what I've just said about those things there. Okay. So the first one is electrical conductivity. And we're going to go through these. I'm going to keep it as a column. So, conduct as a solid as the negative electrons are free to move. Okay, so one thing I could have put there is I could have said, electrical conductivity requires charged particles that are free to move. I'm going to put this in my answer. Okay, so zinc chloride does not conduct as solid as positive Zn2 plus and negative Cl minus held in place too strongly. Conducts when molten, which means melted, or in solution as the ionic bonds are overcome, broken. Okay, so that means ions are free to move. Okay, last bit. We're getting through it pretty quickly. So you notice that there's not much to say about the electrical conductivity of a metal. The only thing I probably could add there is just a comment that the positive zinc nuclei or ions are still fixed in space. fixed in place. That just, I suppose it just adds a little bit more detail. That shows that I understand that, yeah, it's the electrons that are causing conduction, not the cations. Okay, my last property, if I go back to the top, is solubility in water. Okay, now for this, I'm going to cover something that we haven't done in class yet. And I'm just going to quickly draw a water molecule over here. And what we've got here is a delta positive side and a delta negative side. Now, the reason that zinc chloride is soluble is that the zinc ions are attracted to the negative side of it, and the chloride, let's be specific here, chloride ions are attracted to the positive side. So, this attraction allows the ions to be removed into solution. So that's what I've got to say in my answer. So, I'm going to say H2O is a polar solvent, because that's one of the things that the question's actually after, I'm sure. Okay? Zn2 plus ions are attracted to the delta minus pole, so this is what polarity means, pole of water. And Cl minus is attracted to the delta plus pole. This overcomes the ionic bond, so zinc chloride is soluble. Now, I know I said that that there are zinc ions in the metal as well. However, the overall effect is that in the lattice there is no charge there. Okay, so if I have a look over here, the metallic lattice is not overcome. Actually, I'm going to rephrase that, sorry. Okay. I'm going to say that zinc does not dissolve in water. So I'll say that it's not soluble first. As the attraction between the particles and water and I would put in brackets Zn, which shows there's no charge there. Water does not overcome the metallic bond. Okay, and there we go. I've used a bit more space than actually given there. But as we know, in NCEA, there's often spare paper at the bottom as well. Okay, so just going through that whole question again. Without explaining it, I would expect it to take 15 minutes to answer, but explaining it, it's taken me a bit more. When you have a table, make sure you identify the type of substance that it is first, before you try to fill in those spaces. For an explain answer, try to be concise, just get to the point. So high melting point means that it's got strong bonds, so now you need to say why it's got strong bonds. A low melting point, conversely, would mean weak bonds, and we'd need to talk about that, so that would be molecular, for example. Then when we've got a contrast or a compare and contrast, you know that you're looking at what do they have in common and what's different about them and why, so linking that to structure and bonding. And here, make sure you actually do say something about what's required for electrical conductivity and what's required for water solubility. Electrical conductivity, I've said it inside my answer that we need charged particles that are not held in place. And the water solubility, I've shown there has to be an attraction to the water molecules to make it soluble. So I hope that's helpful and gives you an answer for this one.